So let's talk about the agenda. We'll do some questions. We're going to finish section 2.4. We'll finish today with the homework quiz. So that'll come at the end.
Is it going to be on 2.4?
No. But I'm doing it at the end, so like if you finish early, you just can start homework. If you've already caught all the way up, we'll have the 2.4 stuff that you could work on. Rather than like doing it right away, and then you sit there and twiddle your thumbs, and you have to wait for the last person to finish before you get to hear more stuff. So that's the decision I made. Okay. Anyways, but we're just going to start with questions. Anything you want. Who's ready? Tommy, you had your hand up first, it seemed like.
31.
31. I thought I grabbed both pages. Apparently not. All right. 31 says to do this without your calculator. So first thing I would do is pi over 6 is obviously a radians angle measure. I'm going to convert that into radians. What do I have to do to convert something from degrees to, or from radians to degrees? Multiply by 180 over pi. That's a good thing to remember. So when I do that, I get 30 degrees. So this is really the same thing as sine 30. Oh, 30 degrees. I recognize that guy now. That's part of a 30, 60, 90 right triangle. So when I write in my side lengths, they're x, x root 3, and 2x. So if I use SOHCAHTOA, opposite is x, hypotenuse is 2x. That reduces down to 1/2. Yes. Uh-huh. But if I ask for something without a calculator, I'd want to see this. This would be the work that I'd need to see if I asked you to do something without a calculator. You know what I mean? Doesn't mean that like you can't have a calculator to do it. It just means that like I'm looking for specific work then to show you, like show me how you did it without a calculator. You know what I mean? Tommy, does that feel good to you? So probably just remembering to convert that thing into degrees so you can draw your special right triangle is probably all that you need there. Who else has got something for Mr. Gulick? Talika? 22, you say?
Yeah.
Okay. Well, 22 is probably the trickiest one on here. So it says two toy racetracks form concentric circles. So again, concentric circles means like one circle's inside of the other. Each track is divided into 25 identical sections. So I'm just going to draw, I said 15 identical sections. I'm going to draw one of those 15 identical sections here. Is that cool? I'm not going to draw all 15 of them because it feels like, I'm going to get too busy. It says, if the inside car travels 1.2 centimeters less than the outer car on each piece of track. So there we're talking about like this length S1 and this length S2, we'll call them. Set up two equations using arc length formula, use substitution to solve, yada, yada, yada. Okay. Oh, how much bigger is the radius of the outside than the inside? Okay. So R1, R2, and we have a theta here. Cool with the picture we've drawn? So I can say that S1 is equal to R1 times theta, and S2 is equal to R2 times theta. That's going to be the system of two equations that I'm going to solve. Cool with that? If I look at that system, there's a problem though, right? How many equations do I have? 2. How many variables do I have? 5. S1, S2, R1, R2, and theta. 5 variables, 2 equations. Can I solve that specifically? No. All right, well, let's go back to the problem. It says that each track is divided into 15 identical sections. Oh, that tells me something. That tells me that my theta is going to be one full circle in radians. How much is that? 2 pi. So each one of those is going to be, angles is going to be, the full circle divided by 15. Okay, well that's good. It says then the inside car travels 1.2 centimeters than the outside car. So S1 is equal to S2 minus 1.2. So let's go ahead and add that in and see where we're at now. So we have S2 minus 1.2 equals R1 times 2 pi over 15. And then S2 is equal to R2 times 2 pi divided by 15. How am I doing now? How many variables do I have?
2, 4.
3. I have S2, R1, and R2. Everybody okay with that? Does it matter that S2 occurred twice? Not to me. Okay, well that's still kind of a problem, right? Because to solve this precisely, I need to have just 2 variables in 2 equations, right? But let's take a little bit closer read. Was it really asking us for? So what it's really asking us for is what R2 minus R1 is. Oh, okay, well those really count as the same variable then, right? Because if I just solve for what R2 minus R1 is, that's my answer. I don't actually need to find the values for R2 and R1. So that'll be okay that I have 3 variables in there. All right, well I'm ready to rock and roll then. I'm going to do my substitution, so I'm going to sub in S2. So I can say R2 times 2 pi over 15 minus 1.2 is going to equal R1 times 2 pi over 15. Just doing a substitution. I'm going to add the 1.2 over and subtract the R1 over. Cool there. I can notice I have a greatest common factor of 2 pi over 15. I can factor that out. Hey, there's my R2 minus R1. And then I can multiply both sides by the reciprocal. And then it's just calculator time, right? So whatever that comes out to be, I'll let you handle the buttons. Is that cool though? Yeah. So the tricky part was there that you didn't actually ever find R2 and R1 specifically. You just found their difference because that's all it was really asking for. And in fact, with the information you're provided, there is nothing you can do to get R2 and R1. Ooh. Just as a separate aside on my picture, what is R2 minus R1? It's that distance, right? Olivia. Well, I mean, it could be.
Is it?
Why? You know, it's a surprise.
Yeah, great over time. What? You were saying.
And then you said 24 as well, Talika, right?
No, I'm going to Jacob first.
A circular saw has a diameter of 8.25 inches and there are 12 teeth per inch on the cutting blade. The saw spins at 3,500 RPM. How many cutting teeth cross the surface each second? Well, this is just like a unit conversion problem. So I'll start with the rate that I know we're going at 3,500 revolutions per 1 minute. And when we finish up, we should be in some teeth per second. Well, I'm currently in minutes. I need to be in per second. So let's just go ahead and do that conversion first because that's really easy to do. I know exactly how to do that. Everybody agree with that? All right. Now I need to get to revolutions, or from revolutions to teeth. Ugh. Well, I remember that 1 revolution is equal to 1 circumference, right? So in this case, I know 1 revolution is diameter times pi inches. So I can say 1 rev, 8.25 pi inches. So now I'm in inches per second. I want to end up in teeth per second. What else is there? Oh, 12 teeth per inch. Guess what that is? It's another unit conversion. Oh, it just tells it to me. So I know 1 inch has 12 teeth. So now inches cancel, and I'm left with teeth per second. All I got to do is grind that multiplication through to my answer. So not too bad, right? Sophia. 23? I mean, it's like the same problem, isn't it? Okay, so you have 14 miles per hour. And you got to convert that down into revolutions per minute. Well, I'll start by converting hours into minutes. And then I got to convert miles into revolutions. I remember that 1 revolution is 1 circumference. And here that circumference is going to be 22 pi inches. Oh, but my unit for distance is in miles. All right, let's convert miles to inches, I guess. 1 mile is 5,280 feet. You guys all know that, right? Oh, that's a common one. You should know that. 1 foot is 12 inches. And I know that 22 pi inches is 1 revolution. And then that's going to be good, right? So miles cancel with miles, feet with feet, inches with inches, and then hours with hours. So I'm left with revolutions per minute. And I think that's should do me. Does that feel okay, Sophia? It's like almost the exact same setup as the example problem in the homework or in the notes. It just didn't have to go quite as far because we went minutes instead of per second. Olivia? Sure. So pizza shop worker decides to cut a round pizza into 10 equal slices. Okay. So I'm just going to draw one of the 10 slices. The diameter of the pizza is 8 inches. So that means that this piece has radius 9, each of those, right? The pizza's diameter is 18. Those have to be 9-inch radii. And it says, what is the length of each piece of crust? So I'm looking for the value for S. I know S is equal to R times theta. The R in this case we know is 9. Theta I can find the same way as I did on 22. Again, I'm going to use the radians version because the arc length formula is easier. So there's 2 pi in a circle. We're dividing that circle into 10 segments. So pi over 5. I just reduced. And then you just multiply it through. Bada boom, bada bing. I think if you got into the 40s, I think you should be should be good. I think we ended, section 2.3 I think ends at like 44 or something.
Gotcha.
If you're up through there, you should be plenty good. Anybody else? Sophia, you said you had a lot of them. You only asked one, though, I think.
I'm trying to find the ones that are-
Oh, okay. I appreciate when you give me a warning, though, beforehand.
47.
Well, we shouldn't be doing those yet.
Oh, did you not say that?
No, I think if you got 44, you're fine. So we'll finish anything past that today.
Okay,
All the stuff past that is 2.4 stuff. We didn't finish 2.4,
Okay.
so that's fine.
Yeah, I did not understand how. Yeah.
Olivia.
For 43 and 44, it says like the one has to be negative, which is just like the opposite.
Yeah, I would just
And
subtract.
then you subtract 3.
I would just subtract 360s or 2 pi's until I got a negative one. Yeah. And if the first one was negative, then I start over and add to get the positive one. You know, like, just that's all. Jake.
You did 34. I know you did 34.
Yeah. So 34. Wow, we're feisty today, guys. So I'm going to do the same thing. I'll start by just converting this into degrees. So that's the same thing as 45 degrees. So if I draw my 45, 45, 90 triangle, the side lengths are x, x, and x root 2. I'll just do this. That's easier. And I remember secant is hypotenuse over adjacent, which just reduces down to root 2. Dunzos. Ava, I got your sister's name stuck. I'm like, that's her sister's name. And I was like, what is her name? 43? Oh, 44? Okay. So it says we just want to find a coterminal angle. We want one to be negative, one to be positive. Well, this is already positive, right? If I add 2 pi to that, which will definitely give me another positive result. So when I add 2 pi with a common denominator, that's 14 over 7. So I get 16 pi over 7. That's one answer. And I notice that 2/7 of pi is less than 2 pi. So if I subtract 2 pi from that, I'll also get a negative result. So there's my 2 angles, one coterminal, one positive, one negative. No problem, dude. How you guys doing? I don't think it's going to be that bad, guys. And you're the math teacher. You tell us all the time, like, you just look good at this because you've been doing it for 20 years, the same math over and over and over again. And like, well, yeah, but I also didn't pick, like, I don't usually pick the hardest things possible to put on the homework quiz. You saw last time. Did I pick the hardest things that we did in the homework in the last one? Not really. Ava.
Sorry.
Are you sure?
Yeah.
Okay. Are we ready to start then? I mean, as ready as you're gonna be? Okay. You feel like I gave you a fair shift to ask questions, right?
Yeah.
I answered everything you wanted me to? Did I do it thoroughly enough?
Yes.
Did you feel better than when you started? Okay. We'll take all of those answers. Those all sound good to me right now. Do you still look concerned to me? Yeah, probably, but we gotta still move forward. Yes. Yes, I have 4 of them, in fact. Just sitting here at the edge of my desk. Only get to take 1 per person, though. You can't use 4 of them.
Thank you.
Yeah, I know what you're planning there, Rita. Okay. So, last time Last time, we did some very important stuff. We noticed that in geometry, sine, cosine, etc., theta was a acute angle. I'm sorry. These guys were defined using acute angles in our right triangle, right? That was our geometric definition, right? Last time, we updated this definition. Sine, cosine, tangent, etc. are defined by a point P on the terminal side of a standard position angle. So what did we say there? We said that for some standard position angle, standard position means the vertex of the angles at the origin and the initial side lies on the positive side of the x-axis, and then our angle measure is rotated about starting at the initial side, pivoting at the origin, whatever, like this. So if we pull any point from that vertex, call it x comma y, and we call r the distance from that point to the origin, we said that sine was going to equal y over r, cosine was going to equal x over r, tangent was going to equal y over x, cosecant, no surprise, r over y, secant, r over x, and cotangent, x over y. So these were our new updated definitions for sine, cosine, and tangent that are now based on standard position angles rather than geometric figures. We're now defining all of our angles on this standard position method that allowed us to now draw angles of any size. You could draw angles with measure from negative infinity all the way to positive infinity. Big change from geometry where we're stuck drawing angles between 0 and 180, or even our geometric definition for sine, cosine, and tangent that was restricted for angle measures between 0 and 90, right? Now we can draw anything we want. Let me double check to remember exactly where I left off. I think we might have just said that as the very last thing. Yes, okay. Great. So let's do an example here. So let's say that the point P, well, it's not even, I don't need a name for it. I'll just give it a number. The point -3, 4 lies on the terminal side of the standard position angle theta. Write the 6 trig ratios for theta. What do you suppose I'm going to start by doing? Drawing a picture. Did I do this example last time? I don't think I did. Do you guys remember? You think we did do this one? Oh, did we?
Yeah.
No.
Oh, yeah, I'll do this exact one. Yeah, we did up to the units.
Oh, okay. Oh, so we got to the unit. Okay. Never mind then. Thank you. We'll skip this. We did this last time. Okay. All right. No problem. All right. So what we were at, you noticed with our latest method using the so when we use a point on the terminal side of a standard position angle, we have some freedom of choice there. What do we have a choice of? In this method, what do we have a choice of? Well, not the angle we want to use. Picking P, right? The way we've described this, it doesn't matter where you're picking P at. Everybody agree with this? Oh, come on. We can improve our method here by standardizing how we choose P. How do you suppose we're going to do that? So we're going to standardize this by when we choose our P on the terminal side, we're going to choose P such that the distance from P to the origin will be 1. Okay, Mr. Kulik, who cares? What the heck does this matter? Well, what does this change? Or what does this make constant now? It tells us that the R is always going to be 1, right? R was the distance from the point to the origin. If we're always going to choose our point so R becomes 1, how do our definitions update? Sine theta was y over r, so now it becomes y. Cosine was x over r, so now it becomes x. Tangent was y over x, so now it becomes no change. Cosecant was r over y, it now is 1 over y. Secant was r over x, that becomes 1 over x. Cotangent was x over y, it becomes x over y. Okay, big flippin' deal, Mr. Kulik. Who cares? Well, let's examine a little bit more closely what just happened by doing this. So let's imagine that we want to talk about all angles, all standard position angles. And I want to consider where that point P would be on all standard position angles. So 1 unit from the origin, P could be there, or maybe there, or there, or there, there. I'm just kind of looking at what's going on. Does this look familiar? It's a circle. I see. And specifically, what's the radius of this circle?
1.
So what do we call this thing?
Unit circle. Did we?
Huh? We didn't do it last time yet. We were building towards this. We haven't done it yet. Did you do it in integrated? Probably. Everybody's okay with this? Notice that the points on this circle, these xy's, well, what is x again?
Well, sine.
It's cosine theta. And y was sine theta. So what have we now, how is sine, cosine, and tangent defined? They're defined as, or by, the points on a unit circle. Oh! All right. Sure. So we have three separate definitions that we use at times for sine, cosine, and tangent. We have our old school geometric definition with SOHCAHTOA. We have our terminal side definition. And then we have our unit circle definition. Mr. Kulik, am I going to have to use all those at different times in the course? Yes. Will it be advantageous enormously to use one versus another in certain contexts? Yes. Do we have to be able to do all of them and use them kind of interchangeably, maybe even the same problem? Yes. All right. Let's...
P plus S or P from the
P plus S, PTS for points.
Oh. Okay.
Okay, got flies buzzing around here on me. So what we're going to do next, you should have noticed that we're able to find exact values for sine, cosine, and tangent when we drew our, stop talking please, our standard position angle. If the reference angle or reference triangle we drew was a 30, 60, 90 or 45, 45, 90 triangle, right? Let's collect all of those angles into one place so we can kind of shortcut having to draw these reference triangles over and over and over again. We'll do it like once and then be done with it. Okay. The exercise that we're going to be doing here to do that, I'm going to be filling out what's called a unit circle. Thought I dropped one in here already. I've posted a blank copy in the OneNote. Let me just push through a sync here so that if it wasn't already on your end, if you were following along and you wanted it, it should pop in here in a second. Yes, sir. Yep. All right. Here we go. Stop talking, please. So, we'll start with the super obvious ones. This is a 0-degree angle where both the terminal and initial side of our angle lie on the positive x-axis. That means the point on my terminal side would be this point right here. What's the coordinate for that point? 1, 0. How'd you know that was 1, 0? The radius or the length of P is 1. There's a unit circle, so everybody's cool with that? Let's go here to 90 degrees where the point on my unit circle would be there. What's the coordinate of this point?
0, 1.
0, 1. Okay. Over here is 180 degrees. What's this point?
-1.
Great. And then we'll go down to this spot here, which is 270 degrees. What's the coordinate there? 0, -1. If I went back around, this would be 360 again if we wanted to, right? Okay. Let's do now, say, the 45, 45, 90 triangles. So this point here forms like a 45, 45, 90 reference triangle. So when I do that, I'm going to call these side lengths A's. The ratio of side lengths should look like this, right? What value should I pick for A here? Nope. I need this length to be equal to 1, because that's the radius of my unit circle. So what does A have to equal? 1 over the square root of 2. I'm just going to leave it that way for now. You can rationalize later. So this piece is my x coordinate. This piece is my y coordinate. So since they're both just A, those are 1 over the square root of 2 in both places. Everybody's cool? And since we're in the first quadrant, the x coordinate is positive and the y coordinate is positive. If you want to rationalize those, go ahead. I'm going to leave them unrationalized for right now. Of course. Okay. This spot here at 135 will also make a 45, 45, 90 reference triangle. The x coordinates and y coordinates are going to be the same, except for, because we're in quadrant 2, the x coordinate will be negative. The y coordinate will be positive. I'm just going to go ahead and write negative signs next to the x coordinates and all the things in quadrant 2 right now. I'm thinking about it. The next piece down here is 225. Since we're in quadrant 3, the x coordinate is negative, and the y coordinate is negative. I'm going to go ahead and write in those next to everything in quadrant 3 as long as I'm thinking about it. And then my last one is over here, 315. Since we're in quadrant 4, the x-coordinate here is positive, but the y-coordinate is. I'm going to go ahead and write my negative signs in next to all of my y-coordinates in quadrant 4. Does everybody feel good so far? Okay. Let's go through and do our 30-degree, our triangles with a 30-degree reference angle. Okay. So what value should I pick for A in this case? Yeah, A needs to be 1/2 because, again, the hypotenuse of my triangle needs to be the same length as the radius in my unit circle. So A has to be 1/2. That means my x-coordinate has to be √3/2. And my y-coordinate has to be 1/2. Everybody feel okay there? Zoom in a little bit better so I can write that a little bit clearer. Okay, so oh boy. The next place where we have a 30-degree reference angle is over here at 150 degrees. So the x coordinates are still the same, and I already took care of the signs all when I was here last time, so I can just copy in the x and y coordinates. The other place where I'll have a 30-degree reference reference angle is down here at 210. Copy in my coordinates. And then again over here at 330, again, I'll copy in my coordinates. Nolan?
I'm just confused, because like the y values, if 1/2 is the y value for like the first point, and then it's 1/√2 for the second point, wouldn't 1/√2 be lower than 1/2?
1/√2 is like 0.707. So that's higher than 1/2. √2 is about 1.41. So 1/√, am I correct there?
Oh, yeah.
Okay. That's okay. I'm glad you're double checking and thinking about, like, does this make sense? That's good. All right. We have one more set of angles to do, and those are going to be where a 60-degree reference angle is formed. So I'll draw my picture. So here we have A √3, and 2A. What does A have to be here again? 1/2. But this time the x is 1/2 and the y is √3/2. Everybody's cool? Again, because this is my x side and this is my y side. Okay, let's go and fill in the last pieces here. So I have 1/2 and √3/2. This piece is 120, and I have 1/2 √3/2. Again, I'm not adding in the signs because I did that already. Down here, I have 240. Again, putting in my 1/2 and my √3/2. And in the last spot here, I have my 300, and I have 1/2 √3/2. You'll notice there still is one more set of blanks here, right? What do you suppose is this other set of blanks for?
Pi stuff.
The radian versions of these angles. So all I'm going to do is convert these angle measures to radians. So I'm multiplying those by pi/180, so that's 0, pi/6, pi/4, pi/3, 2 pi/3, 3 pi/4, 5 pi/6, pi, 4 pi/3, 5 pi/4, nope, that wasn't right. That's 7 pi/6. Yeah. Yeah. It's like, that doesn't look right. That's not 2/3 of a pi. Oops-a-daisy. And then this is 5 pi/3, 7 pi/4, and 11 pi/6.
Just easy one.
Okay. Nolan.
Is it okay to have squares and integers on these points?
I just wanted to leave them in there because it was just going to make life a little bit less complicated. The reason I left them there is because if you wanted to do r, if you do like x squared plus y squared square rooted, if you use the square root 2/2, you end up getting like What do you end up getting there when you do that? You get like, you don't get exactly 1 when you, it works out to be less convenient. Like when I do this, it's like clearly you're getting 1 because you get 1/2 plus 1/2, which is square root of 1. So like, that's why I do it that way. When you report your final answers, rationalize, but I usually don't rationalize on intermediate steps. And that's what this is. It's just like an intermediate step to doing a problem. So that's why I've just left them that way. The typed out version I have, I think I didn't do that. Let me drop that in for you guys while I'm thinking about it. So here is the full version of the unit circle that I dropped in. Yeah, here I rationalized them when I typed out the full version, but just me personally, when I'm doing an intermediate step, I never rationalize until I'm presenting a final answer. And because this is just a tool to get to a final answer, I usually just leave it. In particular, I think it makes it sometimes inconvenient to do other things, to have the like this root 2 over 2 instead of just the regular old 1 over root 2. But it's whatever. Is that, you happy there?
Yeah.
Okay. All right. So some of us know what the unit circle is and how to use it. Some of us, if this is the first time we're seeing it, right? Let's go through some examples of how we use this to do something, and show you how easy it makes life. All right, so I'm going to just put a copy of the unit circle in. Come on, get out of there. So that I can reference it while I'm doing this. So if I want to do sine of 225, first thing I'll do is see if 225 is on my unit circle. It is. Once I've done that, I remember that sine is equal to the y-coordinate. So I'll just read the y-coordinate off my unit circle. And I'm done.
We get some of the test.
Yep.
Yes.
Yep.
Like we get the unit circle.
Yep.
Oh God.
So what if I wanted to do, say, secant of 405? Well, Mr. Kulik, 405 is definitely not on the unit circle. You're right, but is it coterminal to something on the unit circle? So that should be the same as secant of 45. So if I go to 45, secant, I remember, was 1 over x. This is why I like to do it my way, Nolan. So 1 over x is going to be the reciprocal of x, which just reduces down to root 2 over 1, or root 2. If I had it the other way that I'd written it just, you don't have to rationalize. Or reduce, actually. I'd rather rationalize than have it to reduce something like this. But that's me personally. What if I wanted to do, say, tangent of negative 120? Well, negative 120 is not on my unit circle, but it looks like it's coterminal to something on my unit circle. That's good enough. So let's locate 240. There it is. What is tangent again? It's y over x. And when I reduce that, I get just root 3 over 1, or root 3. So what is the unit circle really? It's just a shortcut to finding the exact values for sine, cosine, and tangents, so we don't have to draw a reference triangle and like build out our 30, 60, 90 or 45, 45, 90 triangle and make sure we have all the signs correct for the correct coordinate. It just allows us to skip through all that crapola. We did it once to construct it, and we'll use it as a tool, a shortcut, to get around from having to draw those pictures every time. Is everybody cool with that?
Yes.
Yes.
What if we get like a degree or something, and it's not coterminal to anything, and it's not a Riemann circle?
Probably just have to use our calculator.
Okay.
And we'll talk about that in the future.
Got it.
Or it might be something that you can still do with some tricky formula that we'll get in the future.
Oh, okay.
But not always. So like I could do tan of 22.5, but I couldn't do tan of 22.4.
Okay. Oh, we'll learn that later.
It's a future. That's a far in the future thing. All right, I got one more example, and then we're dunzos here. Yeah. Dunzos. I meant what I said. Yeah, right after this example.
Will it be enough time though to finish?
Yeah.
How many questions are there?
3.
I can't do that.
The more talking you're doing, the less time we're going to end up with it. Get your belly aching. All right. Let's say we want to find sine theta if cosine theta is equal to 5/7 and cotangent theta is less than 0 if it's negative. First thing I need to do is figure out where to put my terminal side in my picture, right?
Okay.
Well, I remember that on the unit circle, cosine is equal to x. And since this is equal to 5/7, I know that x is positive. So that tells me I'm either going to be working in quadrant 1 or quadrant 4. Everybody agree with that? Cotangent is equal to x over y. We've already established that x is positive. So a positive over y giving me negative implies that y is negative. So that means we'd have to be in quadrant 3 or quadrant 4. So what quadrant does my terminal side have to be in? Quadrant 4. So that's got to be the angle theta that I'm talking about, or at least coterminal to that one, right? Everybody happy so far? Okay. So if I draw in my reference triangle then, I know that the adjacent side is 5 and the hypotenuse is 7. Everybody's okay with that? How can I find this opposite side? Pythagorean theorem. So I know 5 squared plus y squared is equal to 7 squared. So 25 plus y squared is equal to 49. Y squared is equal to 24. We'll square root both sides. We'll reduce that radical. The square root of 24 is the square root of 4 times the square root of 6, or 2 root 6. Does that all look good so far? It shouldn't. I've made a mistake here on purpose.
Negative?
Yeah, what should be negative?
7.
Nope.
Or 2.
2 root 6. Remember, the 7 is always a distance, right? The r is defined as the distance from our point to the origin. That will always be positive. the x or y values that are these side lengths are proxies for can be negative. So now if I do sine is going to be y over r, and I'm done. What do you guys think? Solid. Little bit of practice and you'll be a pro in no time.
I'm already a pro, so don't worry.
You can add into your problem set. You guys can now do 45 through 60.
60.
Yep.
6.